All right, we'll finalize this list. And according to our rules, we should have a 3-team physics match for the finals, right? And we will have the team that is ranked 3rd place being the reporter first. All right, so let me just check on the our official regulations to confirm that. So in stage number 1, the reporting team will be team UTS 5. The opposition team will be team affiliated. And the reviewing team is team UTS Shroomskis. Is that fine with everyone? All right. Let's just make sure that these teams are here. Is UTS 5 here?
Yeah, I'm here.
Yeah, sorry. We are here.
Yeah, sorry about that.
Is team affiliated here?
Yes, we're here.
And is team UTS Shroomskis here?
Yes, we are.
All right. So I think we can skip this opponent challenge, the reporter stage. Okay, just go to the next phase. Yes. And we can skip this accept or reject too. And we'll go straight into the 5 minutes preparation of the reporter, and that will be a team member of team UTS 5. You have 5 minutes to prepare. The problem is rigid ramp walker. And I would like to ask the jurors, please send, upload your score sheet into the Google Drive that we have provided immediately after this match. So we will be able to tally up the scores. So we have about 15 seconds, well, actually 10 seconds left before we have to start. The reporter,
yeah.
could you please
I'm ready.
share your screen? Yes.
Yeah. Okay, here we go. Screen. And here's the presentation. Can you see the presentation?
Yes, we can.
Okay, wonderful. May I begin?
Please start whenever you're ready.
All right. So, hello, I'm Ben Granega, and I'm representing UTS Physics and Style, or UTS Team 5. So, and this is problem number 3, rigid ramp walker. So, construct a rigid ramp walker with 4 legs, each in the form of a ladder. The construction may begin to walk down a rough ramp. Investigate how the geometry of the walker and relevant parameters affect its terminal velocity of walking. And on the right here, we can see the phenomenon in action. So some parameters that we'll be looking at today are the ramp walker height, the leg length, and the step length. So you can see the parameters here. So in this presentation, we'll look over the experimental setup, the theoretical model, key parameter interactions, and a conclusion. So here's the phenomenon again. So some preliminary observations that the walker rocks along the x-axis, or along the axis that it's traveling down. The walker's legs swing on one side at a time. The walker's legs on one side swing in unison, and the sideways rocking of the walker is directly correlated to the step of the walker. So the ramp walker's step can be divided into 2 mechanical processes, which is the side-to-side rocking of the walker and the swinging of the walker's legs. So the side-to-side rocking of the walker is used to clear a pair of legs off the ground and enable them to swing, as you can see here. And the swinging of the legs is done in unison and follows the pattern of a simple pendulum when falling, and this is just because of the geometry of the legs. Then the rocker continues to rock side to side because gravity acts as a restorative force, and the rocker continues to rock side to side using simple harmonic motion. So this experimental setup, we have the ramp walker, this 3D printed ramp walker, a tracking point, which are marked in yellow. There's notches for ramp inclination, and here's the wooden ramp. So now a closer look at the ramp walker that I designed. So it has a step length adjuster to adjust the step length. We have the legs, there's the hip joints here, and then there's these semicircular feet. And the legs and the rest of the legs are the highest point in the body. So the measurement method that we used was the tracker software. So you can see right here, we just track the point over time. So now moving on to our theoretical model. So there's 3. The first one that I'm going to be talking about is using harmonic motion for sideways oscillation. So some assumptions that we make. First of all, air resistance is not a major factor. It's a very small mechanical piece with very little surface area. And the second thing is that the walker doesn't oscillate further than 15 degrees on either side. This is important for some of the calculations that we use. The formulas only work in this range. And the reason why we assume that it doesn't oscillate further is simply because mechanically, if it were to oscillate further, the ramp walker would tip over. So the geometry here, just to clarify, the green line here will be used as the x-axis, the blue line as the z, and the orange as the y. And then for this model, we'll just be looking at point A, and point A is this front leg tracking point. So here's another look. Point A again is right above the leg, and the leg amplitude swinging back and forth is around 1.5 centimeters, and we just calculated that using the geometry of the walker. And then the height of the walker in this case would be 10.6 centimeters. So some basic principles. We'll be using for the formula for the frequency of oscillation for a basic pendulum, and then also the formula for the position of a pendulum along the y-axis at any point. And these are both based on simple harmonic motion. So you can see a combined formula would look like this. We also use angular frequency to put this into this formula. And then with our dimensions, we end up with this formula right here. And so here is the experimental verification. We have on the red line is a median of 3 ramp walker tests, while the blue line is the predicted walking. So now we're going to use harmonic motion for leg swinging. So some assumptions, again, that air resistance is not a major factor, as we went over before. And the other thing is ramp walker leg may only swing if it's cleared from the ground, and the ramp walker legs swing in unison, as well as the ramp walker height should be equal to the ramp walker leg length. So basically, the first assumption is that when the blue foot is on the ground, the red foot can swing and the blue foot won't swing, and obviously vice versa. And I mean, it's pretty self-explanatory, but it's just to make sure the velocity readings are correct. Now, for the positions of point A and B, you can see that they do swing in unison. So you can see that this is the graph of point A over time, so the distance from the starting point over time, and you can see that they both follow a very similar step cycle. So now the other assumption is that the legs are not below the tallest point of the walker, and this is so that this period of oscillation, side-to-side oscillation or rocking, is the same as the period of step length. Again, the geometry right for this problem will be using the x-axis and the front leg pivot, which is marked in blue, and point A. So here's another look at the geometry of the leg, a closer up look. So it can only swing. We limited it to 11.3. This we found was the most effective. And so it has a total amplitude of 2.8 centimeters. So we use the same basic formulas to predict the pendular motion of the leg, with the addition of calculating velocity. So from here, this is the combined formula of the velocity of the ramp walker plus obviously the above mentioned theories for the simple harmonic motion. And so you can see as experimental verification, we have the calculated velocity in blue and the velocity from the experiment in red. So you can see they're very similar. The only difference is we have these peaks forming, and these are due to slippage. So we don't have a perfect grip on the wooden surface just because of the legs, because we use electrical tape on the bottom of the legs, and so that's why this is caused. So now final theoretical model is about the total distance traveled. So we assume that the increased distance traveled due to friction is minimal, that the dampening is not accounted for, and that the walker legs swing in unison. So again, we can see the same geometry as before. So we'll be using the formula for velocity, and then we convert the velocity readings into the distance traveled by point A, and then from there we can calculate the total distance traveled just by taking the total distance traveled is from one point in time, and the velocity at another point in time. So you can see this is the meeting position of point A over a series of 3 tests, and here's the estimated in blue. And so this displacement is due to multiple factors such as dampening and also this slippage, as we saw before. So some key parameters is the height of the ramp walker, the length of the legs, and the step length, which affect the oscillation of the ramp walker along the x-axis, the step period, and the step amplitude. So we've first varied the height of the ramp walker. When we decrease the walker height, we increase the frequency of oscillation. And this we can confirm. We can see that a shorter leg length increases the rocking frequency. So you can see with 106 millimeter legs, it has a frequency of 3 over 1.5 seconds, while with 96 millimeter legs, it has a frequency of 3.5, almost 4. So varying leg length is the second. So decreasing the leg length will decrease the step period. Sorry, it should increase the step period. No, it should increase how quickly the legs swing back and forth. So shorter leg length is a faster step period. So you can see here, again, step period, the velocity is 3 steps with the 106 millimeter legs, while 4 steps with the 95 millimeter legs. And now finally varying the step length. So increasing step length increases step amplitude. In this experiment, we increased it so that there was no limit on step amplitude of the front leg. And so we can see in this case, the amplitude with no restriction on the leg length is higher than when it's restricted to 28 millimeters. Now, as you can see, there's a pretty big discrepancy in this graph here with this large drop, and that's because of the leg slipping back, because the step length basically increases past the point of the rocking, and so the step basically swings back, while all the other ones it swings forward and doesn't swing back. So as a conclusion, I'll just restate the problem statement. Construct a rigid ramp walker with 4 legs in the form of a ladder. The construction may begin to walk down a rough ramp. investigate how the geometry of the walker and relevant parameters affect its terminal velocity of walking. So in this experiment, we collected accurate data using a custom-made ramp walker. Experiment allowed us to manipulate leg height and overall height of the walker, as well as step length. And accurate data was collected using tracker software. So the three models that were used to explain the walking was harmonic motion for side-to-side oscillation, harmonic motion for leg swinging, and a combined model for total distance traveled. Here are my references, and thank you for listening.
All right, so we have questions from the opponent. Jerry's to the next section. Please begin.
Yep. Okay. So first of all, great presentation. Definitely the best model of a ramp walker I've ever seen. So can you go to slide 2? Sorry, I think I may have misread a number. It looks like 95 centimeters to me, which.
Yeah. Okay.
Yeah, just slide 2.
Yeah.
Yeah, for leg length, 95 centimeters.
Okay. Yes.
Oh, sorry, or 9.5. Is that what you meant?
Oh, yeah, it's 9.5. Yes.
Oh, okay. Sorry, I was just really confused. Okay, no problem.
Yeah, of course. No, 95 centimeters.
Yeah. Okay. Yeah, and okay. So what I was confused about is when you decrease the leg length, doesn't the step length also decrease? Wouldn't that be a compounding variable?
Yeah, it is.
Okay. So like, how would you control that when you're explaining?
Well, so what do you mean? When we decrease the leg length,
yeah,
the rocking obviously becomes faster.
Yep.
And also the swinging of the leg becomes faster. But those two things, I don't see, they work in unison with each other.
Okay.
Right.
But on these key parameters that you're testing for, so how would you control how would you found a claim for which one is causing the change in?
Oh, because okay, yeah, I can answer you.
Yeah.
It's basically they're two separate processes, right? So in here, it's just pendulum. So let's say we start with the leg length, right?
Yep.
So this is a graph of the velocity, basically of this yellow point here, swinging back and forth.
Right.
Right? And that velocity is not affected by the rocking side to side. Like, it's not affected by this rocking, right?
Yeah. No, that makes sense.
Vice versa. It's, yeah.
Yeah.
Thank you. And then the reporter and opponent, we're running out of time. So we'll move on to the next stage, which is the preparation of the opponent for 3 minutes, starting now.
Ben, you're still sharing your screen. You may want to end the screen share. Yeah.
I apologize for the screen sharing.
Proponent, please start your presentation.
Yep. Okay, so this is problem B, rigid ramp walker, and I'm Eric Mao from Team Affiliated. So the problem statement states, construct a rigid ramp walker with 4 legs in the form of a ladder. The construction may begin to walk down a rough ramp. Investigate how the geometry of the walker and relevant parameters affect its terminal velocity of walking. Okay, so first of all, let's talk about the tasks of this problem. So first of all, we have to understand the mechanics of a 4-legged rigid ramp walker, design and construct a variable geometry ramp walker, develop an experimental setup to measure terminal velocity and influencing factors, and conduct experiments and analyze the impacts of geometrical and environmental parameters. Okay, so a summary of the report. The theoretical analysis, the reporter presented theories for harmonic motion for sideways oscillation, harmonic motion for leg swing, and the total distance traveled. And in the end, he came to a conclusion on the with regards to the relevant parameters that affects the terminal velocity of the walking speed. And as he varied walker height, step length, as well as the length of the legs, and utilized tracker to verify model, which had slight discrepancies on the x-axis due to the possibility of slipping. Okay, so so as for the merits and possible next steps, first of all, this was by far the best design of a leg walker I've seen. Most leg walkers online utilize a cardboard. I think this is the next step for a walker design. I particularly liked how you were able to adjust the variable specifically in the walker. And then another thing is varied relevant key parameters and identify the most important parameter. And there were great diagrams to support the explanation, as well as a very organized slideshow. So some possible next steps or things I would want to discuss is how you guys control the sideways movement of the walker. So I know in these assumptions, we assume that there's only movement in the x-axis, but in this case, if you're setting a walker down a ramp, there's also possible movement in the z-axis. So I would like to know a bit more about that. And then I want to discuss the large shifts in the x-axis of the experimental versus theoretical due to slippage. And perhaps this requires a better rough ramp. And yeah, I would like to yield the rest of my time for the discussion.
Okay, do you want me to share my slideshow?
Yeah, that's good.
Yeah. Okay, here we go. Trying not to share Discord this time. Yeah, I think it should be running now.
Yep, I can see it. Okay. Yeah. So first of all, I would just want to ask, because we ran into a shift on the x-axis too due to the slipping. I know both of us probably didn't have enough time to figure out, but just if you had more time, what would you do to maybe better experimental design to solve this?
Yeah. So I think I have a few ideas. I mean, one of them is changing the surface of the ramp. So possibly coating the ramp, either making it more rough, so with sandpaper or something like that, or a rubber coating, just something to make it grip more. And then for the legs as well, right now I just used the just electrical tape. But what would be nice is to have maybe like an actual rubber piece for the legs, just to add more grip. Yeah.
Okay, yeah, and another thing I want to clarify is what is the actual inner mechanics of the leg? I know it's not like in free motion. There has to be some way you are controlling the or limiting the movement of each leg, right?
Yeah. So what it is the leg itself is connected with a paper clip. So it's just the paper clip axle. So it swings along that axle. And then the actual step length, here's a step length adjuster. It's basically a screw here. and then a piece of plastic on the other end. Or actually, in this case, I mean, it broke, so we just used 2 screws. So it's basically two screws here, which bounces it out. And then as you twist the screws in, obviously this moves closer. And then from that point, you can see, I think, here, you can see how it kind of limits it. So basically, the leg knocks onto this limiter.
Yeah, okay.
And restricts.
Yeah, and the problem specifically stated a rough surface. So like what so how do you guys control for that?
I mean, we just used wood because I think the reason why they said a rough surface is just a grippy surface. So it's to minimize friction, so that friction is not the major factor. In this case, I don't think friction was the major factor, and so the ramp was rough enough for this experiment.
Yeah. So, what are your thoughts on like regarding adjusting the coefficient of friction of the board? How do you think that would affect? Yeah. How do you think that would affect the terminal velocity?
So how would I adjust that? I would, as I said before, probably coat it in rubber or have some piece of rubber tape run along the bottom of the board. Possibly also just adding sandpaper on the top. I think there's multiple ways to do it, just to make it more rough and more grippy. I don't think.
Yeah, sorry. I was just wondering, like how you would think that would affect the terminal velocity. Like,
terminal velocity. Yeah, so it would. It would increase. I mean, obviously, the terminal velocity would see a slight decrease because of the fact that there's no more slippage, right? So there would be a decrease in terminal velocity.
Okay. Yeah. All right. And okay. Can you go back to the slide where you I'm not sure which number this is, but basically it was a velocity time graph comparing the 95 millimeter legs to the 106 millimeter legs.
Yes. Here we go. This one.
Yeah. Can you explain the dip into the negatives on the shorter leg length?
On the shorter, I don't think the shorter leg dip. You mean the longer leg?
Yeah. Sorry. Yeah.
So this happens because when the rocker, so I think the best way to explain it is here. When the rocker oscillates back and forth, obviously because the experiment isn't perfect, it would oscillate more to one side than the other, or it would oscillate more at one particular moment just due to the ramp surface being imperfect. And this would mean that the leg would have a larger distance, or it would have more time to basically swing, and so it would swing further than it should, and then swing back. And when it's swinging back, that causes the negative velocity.
Okay. Yeah. And what do you think is the root cause for the legs to actually swing? Because this is unpowered, right. So
so the root cause is just gravity. It's like a pendulum. Imagine. I mean, I think you've taken physics, so you can see just when you drop a basic pendulum, right, it falls down, and it's just gravity pulling the pendulum down, and that's the same forces acting here.
And out of all the parameters that you've investigated, which do you think is the most important one?
The most important?
Yeah.
It's a good question. I think the leg length would be the most important parameter because you can see here this had the most effect. So, leg length and total height, they work hand in hand with each other.
Right.
And I think these have the most effect because they make the ramp walker oscillate faster, and so it can complete more steps. I do think, though, that it is you have to find a balance between 2 short legs, and then the benefit of rocking is minimal because it's hovering shorter distance, and 2 long legs, in which case it just takes too long to oscillate back and forth. And I think it has more of an effect in step length because you can see step length. I mean, there is a change, but it's quite minimal in amplitude then.
Okay. Yep, I see. Okay, so another variable that we tried to test for was the actual length of the body of the of the ramp walker. So if you were, yeah, so if you had the ability to test for that, how do you think that would, like, the ratio of the length of the body to the length of the leg? How do you think that would affect the terminal velocity?
So length. Well, let me go back to this graph.
Yeah, just
So length or width,
yeah.
because
sorry, length, like in the x-axis.
Okay. Honestly, I think the only effect that it would have would be an effect on the gravity, so center of gravity, basically moving it up, and it would also be heavier at the top. I think that would probably, it would either have no effect or it would make the ramp walker more unbalanced. I don't think the effect would be significant though.
Okay, and yeah, and speaking of weight distribution, did you guys control for that, or in the experiment? Like, I'm assuming the center of mass is in the middle of the ramp walk.
So we assumed for these experiments that the center of mass would be, you see where the x-axis line is?
Yep.
Basically right along this line, if maybe a little bit lower, but in this general area. We didn't test for it, but we assumed that just because this is where there's going to be metal parts, the bulk of the ramp walkers here, and then the legs are quite light, especially because they're plastic, which is air filled.
Okay.
So we assumed that the center of gravity is along this x-axis, and yeah, we didn't test for it, but that's what we used to calculate, and it seemed to do the job pretty well.
Okay, yeah, and I actually want to go back to a point I brought up in the questioning. I was just wondering, how did you guys I know you guys made an assumption that the ramp walker only moves in the x-axis. Did you guys like, when you were testing, did you guys notice any significant movement in the z-axis where, like, it wouldn't go perfectly?
So it happened when the ramp walker wasn't calibrated properly, or there was some issue with the ramp walker just making it one-sided. So it's not an issue with the phenomenon itself. With a perfect ramp walker, there would be no movement along the z-axis. It's just in experiments, in all these experiments that are seen here, the movement along the z-axis was minimal. But yeah, in other experiments, especially if it wasn't set up properly, I mean, obviously it's going to tilt to one side or the other based on deformities in the ramp and stuff like that, because it would change how it oscillates, and it would change. I mean, there's multiple factors that would change.
Yeah. Okay. And while you guys were calculating this, did you guys assume did you guys assume different discrete phases? So what I'm talking about is like for example, a phase would be like when one of the legs is ready for touch and stance, and then, or when it's swinging. Was that?
Yeah. So that's a good question, and we did. It's not a perfect, but as you can, like a perfect calculation, but you can see here we assumed basically once the ramp walker like is touching the ground. So here's the calculated velocity, right?
Right. Yeah.
We assume that once the like touches the ground, it's not going to move.
Just make sure this is the total. This is the velocity in the x-axis, right?
So no, sorry, I should have. This is the velocity of the leg swinging.
Oh, okay, right, okay, yeah.
So you can see we basically assumed that once the leg touches the ground, its velocity would be 0, right? So that would be our phase. It was very simple, and it obviously didn't account for the slippage, but this is what we calculated. It's basically, we only calculated when that leg was moving.
May I have your attention, please? It is now 4:45 p.m. and the light.
Okay. I'm just gonna
If you're borrowing,
all right. Okay. I think time's up, so we will move on to the opponent summarizing the discussion.
Sorry, can I just have 10 seconds for the...
Sure. Sure.
Okay. Okay. So now I'm going to proceed to summarize the discussion. So this is a very fruitful discussion for me personally too, because I came in here having a lot of the same problems that was exhibited in the presentation here. So we discussed how to control for movement in the z-axis. Because universally our models assume that there was only movement in the x-axis. We also talked about the discrete walking phases. Something I didn't get to bring up was quantitatively to determine the phase change from one to another instead of just qualitatively determining it. And also we addressed the misunderstanding about the confounding variable of the leg length and the stride length. So sorry.
All right, thank you. And then questions from the reviewer?
Yep. Thank you guys so much for that. It was a really well done report and a very fruitful discussion. I have a question for the both of you. First, for the reporter. Since you both agree that there is a terminal velocity, what would you say is the primary damper in the system that removes energy?
So I think the primary damper in this case would be, it's a good question. I think it would be mechanical. Well, a large part of it would be the mechanical of the walker. I mean, it's it's using a paper clip. This stuff and move around, it could cause friction. I think that would be.
What about the opponent?
Yeah, I think I'm assuming it's unlubed, so I think there's probably a lot of friction in the joints. I mean, as the only other factor that would be significant would be the air resistance. But I don't think I think the friction in the and the contact force. But I think it's the friction in the joints.
Okay. To the reporter, did you vary the arc of the foot and on each of your feet, and do you think it matters?
I did not vary the arc of the foot. I just basically made it the radius of the feet.
Okay.
Do I think it matters? I think the closer it is to the radius of if a radius was drawn with the height of the walker, I think the more stable.
Okay. And what about the opponent? I'd appreciate some quicker answers because I have a lot of questions to get through.
Okay. So I mean, I didn't vary in my experiments either, but without the arc, you would I don't think the movement would happen. So the arc is in each of the legs is required.
Got it. Okay. To the reporter, did you measure the slipping at all, and did you measure it in the x direction? So did you notice it in the x direction when it was rocking side to side?
Yeah. So as we looked over in our slides before, you could see in the velocity chart where it should be 0, it did spike. So we did measure it. It was something.
And do you think that did you notice any rocking or any slipping in the lateral direction as it rocked down through the oscillations?
Yeah, so as you can see, well, I'm not going to pull it up, but yeah, so we did notice that.
Okay, reporter, could you pull up slide 18 really quick? And in the meantime, a question for the opponent. I noticed in your slides that you said one of the improvements could be that you could control the rocking. How would you do that? How would you propose to do that?
Sorry. I think you were moving. Sorry. I was not referring to the rocking. I was referring to the sideways motion, which is movement in the z-axis.
Okay, got it. And to the reporter, could you explain why your theoretical trend has slight deviations in it?
Yeah. So some slight deviations is of course just imperfect
in the theory
experiment. So you can see obviously.
Sorry, I think we're out of time.
Okay, yeah.
Sorry. All right. Thank you guys so much.
Let's move on to the next stage, which is the preparation of the reviewer for 2 minutes. All right, let's move to the next stage, which is reviewer takes the floor.
All right. Hi, my name is Alan Lian, and this is from Team UTS Stroomskis, and I'll be reviewing problem B, rigid ramp walker. Let's take a quick look at the summary of the report. Theoretically, they went through the qualitative explanation of simple harmonic motion and in their rocking. Their harmonic motion was modeled in both directions, the leg direction and the azimuthal direction, or the rocking, as they described it. And they also went through a qualitative key parameter analysis of each of their three parameters. So their setup consisted of a 3D printed four-legged walker, which could vary the following three things: walker height, leg length, and step length. So, some merits of the report. There was a complete qualitative analysis of the walker's motion with azimuthal oscillations and leg swinging. There's good experimental control using tracker, 3D printed walkers ensuring specifics, and varying key parameters. They had experimental data compared with theoretical formulas, and they had good error analysis talking about the slipping and how it affected their predictions and graphs. Some concerns. There was no explanation of why a terminal velocity is observed, which is fairly important to the speed at which the walker walks down the ramp. They did not attribute damping to the correct source. There was no quantitative investigation into the additional sources of damping, including rolling friction, slipping, and collisions. Finally, there was unclear mechanisms for walker step size. The step size is dominated by the location of the stop instead of the leg length most of the time, and there was a lack of quantitative verification of parameter verification. Finally, there was no characterization of important parameters, such as static friction. Some evaluation of the opponent, they correctly brought up the concern of confounding effective leg length on of the step size and the leg length as a whole. They identified discrepancies in the reporter's theory and experiment, which was attributed to slipping. They introduced the importance of varying friction to the experiment. They explored the effects of varying. Varying key parameters were not fully investigated, which they correctly pointed out. They correctly suggested using a discretized model for the report. However, some concerns with their presentation was that they lacked some of their own opinions and points brought up in discussion. There was an unclear opinion about the effects of some of these parameters. There's a lack of prioritization in discussion, and they also did not point out the importance of the types of friction in the phenomenon and the effects of the cause of terminal velocity and the effect of the ramp angle. And they also brought up some trivial points about controlling the azimuthal rocking of the walker. Some discussion analysis. They went over the controlling the azimuthal wobble. The experimental control of the azimuthal wobble they said was insufficient, and they wanted to control the coefficient of friction. The reporter responded that they would just add sandpaper and electrical tape, which they did, and we agree with the reporter because there was little observed instability in the walker and the rocking of the walker, and sandpaper was a pretty good way of varying friction. The more effects of varying friction, for example, the opponent said that the coefficient of friction is important to the terminal velocity, and the reporter's response was that it was important, and the slipping would increase the terminal velocity. We agree with the reporter that the terminal velocity will be higher. However, the opponent did not present their own opinion on this case. Next, they were talking about the most important parameter to the phenomenon, or which parameter affected the motion of the walker the most. The reporter's response to this question was that the leg length was the most important parameter affecting this period of rocking and step size. We partially agree with the reporter because the leg length does affect the rocking, but it's primarily the height of the center of gravity, which we think affects the rocking and the simple harmonics that take place in that oscillation. Next was the discrete phases. The opponent thought that the model should have been discretized with phases considering the swing step and the swing phase and the standing phase. However, the reporter said that the velocity does incorporate both modes and is sufficient. We agree with the opponent because a discrete model accounts for stick, slip, and different regimes of motion. Thank you.
All right, concluding remarks from the reporter, please.
Okay, so first of all, I'd like to thank my opponent and my reviewer. They both did an excellent job, and I had a very fruitful discussion with them. So, some closing remarks. I mean, in this presentation, we looked over the rigid ramp walker. We saw with the experimental model, 3D printed experimental model, which was quite accurate in good in producing accurate data. So we looked over multiple theories, looking over primarily looking primarily over I'm blanking. You know what? It's probably good to end here say just thank you very much to everyone, all the juries. So yeah, I'll just finish the concluding remarks.
All right, thank you to the reporter, and we can move on to the next stage, in which we have questions from the jury. If you have any questions, please just speak up.
Maybe I can go first.
Yeah, please go ahead.
I have a question for the reviewer. It's just a simple question for the reviewer, that what happens if this complete system is placed in a vacuum?
Very, very little. There would be no air resistance. But besides that, there would be no other effects.
So what happens to the terminal velocity, like in to be specific?
The primary cause of the terminal velocity is the energy loss in the collisions between the leg and the surface. And so that would not be affected by a vacuum.
All right. Thank you so much.
Any other questions from any other jurors?
Yeah, if I could just ask one question each. So we'll start with the reporter. So what if you made the legs heavier? Would that affect the z-axis oscillation?
It depends on what. Well, z-axis, you mean x-axis? Because z-axis.
Yes, you're right. The oscillation, so that's sideways motion.
Yeah. So depends where. I mean, if you put it on the very bottom, right? If you center the mass on the bottom, there wouldn't be any change because the center of mass would stay the same. I mean, obviously, if you raise it, then the center of mass would be raised. And as our reviewer rightfully pointed out, that would affect the rocking.
Okay, then I'll just ask the opponent one question. So you talked about changing the length of the body to leg ratio. If you did that, could you just highlight one or two key results?
Yeah, okay. So we found that the ratio is actually pretty important. But not for but it's for a different factor than the terminal velocity. So basically, the ratio between the leg length and the body length is important, because if that ratio is off by too much, the stability of the ramp walker decreases by a lot. So so at a certain point, the ramp walker will no longer move. The body length becomes too long. But apart from that, increasing the length of the body, actually, we found a positive correlation yes, we found a positive correlation between those variables up until a certain threshold, though.
Okay, thanks.
Any other jurors wish to ask questions?
Sorry, if there's time, can I just ask one more then?
Please go ahead.
Yeah, so for the reviewer, you're talking about sort of changing the curvature of the feet. Did you guys do that, and what were your main findings?
We did not do that, but we determined that the arc of the foot did not matter to the oscillation, because as soon as the foot plants, the other one is the one acting in a part, like the other foot is the part of the phenomenon that actually matters towards the step size and the step length.
Okay, thank you.
I could ask a question. I have a question for the reporter. You said in your presentation that you found that 11.3 centimeters was the optimal length for the legs.
Yeah.
Did you try other lengths? Why was that the optimal amount?
So I tried a large variety of other lengths. The reason why that one works out the best is because that's when the amount that the leg swings forward basically it's not going to swing back after that point, right? So as we saw before, when we didn't limit it at all, the leg would swing forward very far and then swing backwards. At this distance, that wouldn't happen. So it was the most stable.
Thank you.
All right, I think we are out of time for jury question. So let's move on to the next stage in which jurors have 5 minutes to grade. For the finals, to add a little bit of suspense, I guess, we will not ask the jurors to announce their grades or to justify their grade. So after you finish grading, please just send me a message in Zoom to let me know that you finished grading, and please also upload your score sheet into the Drive folder through the same link for the as soon as the stage is done. All right. So just to confirm, first, when you see the final physics match folder, do you see rooms or just 3 stages as folders in that score sheet?
3 stages.
Folder? 3 stages. All right. Cool. Remember always to round your grade to integer.
Wait, question. Do we know who will be presenting next in the order?
As in, like, which team will be presenting next, or
well, I mean, like,
who will
who's
be
going to be
the
reporter, who's going to be opposition, and so on.
right? So, in terms of the next stage, let me just quickly check. So, next stage we should have so team affiliated will be the reporter, and then team UTS-5 will be the reviewer, and team UTS Shroomskis will be the opponent.
Okay,
so perhaps if you want to know who is reporting, you can ask someone from a team affiliated, I guess.
Yeah, okay. Thank you.
Let's just wait for final jurors to upload their scores. So I'm wondering, Mohammed, have you got a chance to upload your score sheets or?
Yeah, I did.
Okay,
It's
cool.
I'm using my middle name, so it's Osama. That's the
Okay,
PDF.
cool. Awesome. Wonderful. Yeah. Okay. Cool. So everyone has uploaded their score sheets. Let me just have a quick check. Okay, page wonderful. All right, cool. That concludes stage 1 of the final physics bash of CaYPT 2024. Let's have everyone take a short break of 5 minutes. Let's come back at 5:13 p.m. Eastern Standard Time. See you in stage 2.
Just want to double check. Tim, are you here? Tim? Doesn't look like he's here. Hey, Tim, are you here? Sorry, we've an issue with our group.
Riz, guys, left more 10 Riz. Let's go.
All right. Hi, everyone. Let's come back. Can we just confirm that the teams are here? Team UTS room seats, are you guys there?
UTS Team 5 is present.
Team 5 is present.
Here.
Room seats here. And
Affiliated is
affiliated. Yeah, all right. Are all the drawers here?
Yes, we are here.
I'm here.
Yes.
Yeah, you can maybe just have a quick thumbs up. All right, cool. And we'll get started. So Jerry, could you please advance the clock to the reporter preparation phase? Yeah, please reset the phase. And in this stage, the reporter is team affiliated, and you have 5 minutes to prepare your presentation. The problem that will be presented is droplet microscope.
By affiliated?
By affiliated, yes.
Can UTS nominate who is opposing?
Yes. So let's just make sure for stage number 1, the reporter from UTS 5. Who was the reporter from UTS 5?
Yeah, sorry, I meant like opposing. Sorry.
Yeah.
Opposing. Yeah, UTS Team 5 was presenting in the first round, and I'm just wondering if we can nominate who from UTS 5 will be opposing.
Yes.
I think we're reviewing. I don't think we're opposing.
Oh, reviewing. Sorry, not opposing. My bad.
Right. Yeah. So okay. So just to confirm, the for stage 1 that we just finished, right? UTS 5, it was Ben that went on stage and reported, correct?
Yep.
And the opponent was Eric, right?
That is correct.
That's correct.
And the reviewer is Alan, right?
Yep.
Right.
Correct.
I was just wondering if everyone could see this.
Yes, we can see your slides.
Okay, thank you. Okay, I guess I'll just get started soon.
All right. And start whenever you're ready.
Also, I'm sorry if there's any background noise because we got kicked out of the library, so if it's loud, please just let me know and I'll repeat. Make it. Okay, I'll start now. So, hi, good afternoon, everyone. My name is Tom, and I'm representing Team Affiliate from Crescent School. And so I'll be presenting problem A, droplet microscope. The problem statement says, by looking through a single water droplet placed on a glass surface, one can observe that the droplet acts as an imaging system. Investigate the magnification and resolution of such a lens. Okay, so the parameters that we have to find as relevant for this problem are droplet volume, also or the size of the droplet, as well as the droplet substance. And I'm also sorry if the slides are slightly disorganized because our PowerPoints got deleted for some reason from last week, so some of the diagrams in here. Okay, so here's an overview of our presentation. So first we have an introduction to the phenomenon, then looking at our experimental setup, so measurement techniques and camera views. Then we're going to be looking at theoretical qualitative and quantitative model, looking at key parameter interactions, and then looking at a conclusion for further insights and general improvements that we can. Okay, so first of all, it's an introduction to the phenomenon. So we can see on the left, we have a droplet that's able to magnify anything from a surface that it's on. And so the reason that this works is because the droplet essentially acts as a convex lens for any object under it. So we can see on the diagram on the right here that the light rays are able to hit the curvature rate surface of the droplet and then be emitted as be magnified essentially for the human eye to see. And so for our experimental setup, this was actually our experimental setup where we actually forgot to take photos when we did the experiment. But essentially we had a tripod with a camera, we had a reference ruler, a borosilicate glass cover, as well as underlighting, and we had cylinders to adjust the height. And so for making droplet toppings, we used an optical microscope, a micropipette, and 3 different types of substances. And so before we look into the experiment, we first want to look at droplet morphology and evaporation profile. So the consistency of these droplets. So we can see that for water, there was an evaporation of water after just 20 minutes, while for the 2 oils that we used, there was no evaporation. And even for immersion oil, after 16 hours, we saw essentially no evaporation. And so this allowed our data with immersion oil to be more consistent, which I'll talk about later. Okay, and our measurement method will be using, first of all, for resolution, we'll be using the United States Air Force 951 resolution test target. And then for size of the droplet, we'll be using image J and processing droplets as via pixels. And so here are the 2 tests we'll be doing. We'll first be looking at the resolution magnification using this setup here. And then we'll also look at some real world application using this other section. And so this is how we measure the droplet size. Essentially, we use the droplets on a digital display with known pixel sizes. And then we were able to use image J to actually model the droplets. Okay, so now into our theoretical model. So first of all, some assumptions. First, we assume that droplets are on a flat, smooth, homogeneous surface, which in this case would door silicon glass covered. We also assume that the droplets are natural convection and they're and the droplet shape is axisymmetric. And so first we'll be looking at droplet profile. Okay, so let's look at droplet characterization. So droplet will be characterized by essentially the Milvos number. And so this describes essentially whether the droplet will be either characterized by a majority of gravity force being domination of the droplet formation or surface tension. So when Milvos number is less than 1, we can utilize Young's equation to model the droplet because surface tension is the biggest contributor. While for Milvos number of greater than 1, then we use a different Seychelles droplet profile. And so these are the variables within Milvos numbers formula. And so let's first take a look at Milvos numbers less than 1. So here we can simply use Young's equation, which describes the model of the droplet via surface tension. This is a pretty standard way of modeling droplets. And so for a CSL profile model, we have the overall number is greater than 1. So we'll be using the Young-Laplace equation instead. And here we're able to substitute in the capillary formula into the Young-Laplace equation in order to get two differential equations in order to solve for the droplet model. We also have a model for the boundaries of the droplet based on its volume. So so where the droplet and so here's our geometry for this. And this was done by Dang and Howard. And then so we use code to basically create this pipeline where we model a droplet, and then we go through these yes or no, essentially yes or no pipelines in order to output us a droplet profile, which we later use to simulate onto the droplet. Okay, now into our refractive analysis, so So first of all, we're going to look at the refractive indices and curvature of each of the droplets. So the refraction of at each surface of the droplet is described by these two following equations, which are pretty standard. And these are the variables. And sorry, I don't have a diagram for this. Unfortunately, it was deleted when we didn't have time to. And so for this problem in particular, we believe that the droplet acts as a big lens, meaning that there are two different areas where the light is where the light is refracted. So first of all, at the surface of the droplet, but also at the area where the droplet and the substrate are touching. And so for a sixth lens, the image formed by the first surface becomes the object for the second surface. And so therefore we can derive this equation for the modified big lens form. And so for our derived focal length and magnification, we can combine the previous two formulas to get a derived droplet focal length, which we'll be using to essentially ensure that our droplets are at the correct focal length for our measurements. And we also use the lens end, so the effective boundaries for our measurements where the lens is no longer reflected. And so third of all, we'll be looking at optical resolutions and our index for measuring magnification and resolution. Okay, so first of all, for magnification, we have the standard magnification formula here. However, since we are considering this as a double lens, we're using transverse magnification formula, which involves two different object and image distances, like I mentioned. From that, we derive the total magnification of the system based on putting in focal length for object distances. And so we were, and since our camera had a fixed focal length as well as image distance, this term is essentially constant, and so we get that m is equal to the following equation. And we also adjusted for depth of field adjustment to ensure that our image was clear. So we have the standard depth of field formula. However, we adjusted it because this is essentially not that accurate for this, since we had two lenses, the droplet and the camera, and as well the droplet was acting as double lens. So instead, we used a more raw formula, where we were able to characterize the farthest distance and the closest distance where objects will appear in focus. And we used the hyperlink and substituted it in to get that the depth of field is this. And for our resolutions, we'll be using the United States Air Force 951 resolution target test function, which is given here by the United States Air Force. And so essentially, this is a method of being able to calculate magnification and resolution using essentially this target test, which we can measure the droplet. Okay, now onto our key parameters. So first of all, for magnification and resolution measurements, so this is the data that we achieved with the United States Air Force resolution test. So we got the resolution was around 24.8 micrometers per line. For our droplet substance and volume, so we saw that magnification increases as the size increases. So essentially, for water and oil theoreticals, we saw that since the oil droplet is more viscous, we saw that it increased the magnification as the volume decreased because it created a greater magnification because it was more viscous, so its focal length was closer. And so here we can see the magnification as we characterized earlier, along with the focal length. And so that makes sense as the focal length decreases, the magnification will increase, and focal length is correlated to the droplets. And so for our resolution, we found that there was actually no correlation. However, we did put a star on it because we believe that the reason we found no correlation is because we were using droplet sizes of a very small magnitude, which didn't allow us to accurately see the full scope of how the resolution will change. So that's something we hope to work on in the future. And so for real-world application, so this was from another study where they used the droplet as a microscope. But essentially, they achieved the resolution of 21 micrometers. This was for onion epidermis. So here they used the microscope on the right, while on the left they were using a droplet as a microscope. And so you can see the differences between the two. So the microscope had a resolution of 100 micrometers, so it was much more accurate for this. But it does prove that we can use droplets in some applications. However, they are not as the resolution and is not as good in that application. Okay, so in summary, these were our variable correlations. So droplet volume had a negative correlation to magnification, while it had a no correlation to resolution. And droplet substance had a positive correlation to magnification and also had no correlation to resolution because of how low the test was. And so in our reflection, we were unable to also test different substrate material due to lack of resources. And for future improvement, we like to test more droplet types and substrate types. And we also like to think the droplet size more to see the true effects on resolution. Yeah. And so in conclusion, here's the problem statement again. By looking through a single droplet placed on a glass surface, one can observe that the droplet acts as an imaging system, investigating magnification resolution of such a lens. And so we created a repeatable experiment. We modeled the droplet theoretically in order to see the magnification resolution through a theoretical model. And then we concluded with the summary of with the correlation following key parameters. And yeah, thank you for listening. And these are our work strategies.
All right, thank you. Now we'll move on to the question of the opponent.
Okay, I'd like to thank you for your report. My first question was, how did you focus your camera?
So we focused it by moving it the appropriate length away from the droplet based on what we calculated for the focal length. Unfortunately the slide wasn't here, but originally I did have a slide where we basically calibrated the camera to have no autofocus on at all. We disable all of it.
Okay, thank you. To measure resolution, did you look at the image by eye, or did you take a photo?
We looked at the we used the photo.
Okay, thank you. What were your settings on your DSLR camera?
I'm sorry, I don't remember them off the top of my head. I had a slide here, but unfortunately, I mentioned, it deleted. But I know we had autofocus off. We had some special about that. I unfortunately couldn't look through.
So that's okay. For your differential equation solving for the shape of your drop, did you solve these equations numerically or analytically?
We solved them.
What were your boundary conditions?
Our boundary conditions were we gave them, which was basically for our boundaries.
Can you hear me?
Yeah. Our boundary conditions were given for the.
Okay. Thank you. Could you go to the slide, your experimental setup slide?
Yeah.
Did you vary the height of your camera or the zoom of your camera?
No. So again, I forgot to take an experimental photo, but essentially it was a lot closer than this. Yeah, it was a lot closer than this, and we did not use this. We used to.
All right, let's move on to the next stage, which is the preparation of the opponent for 3 minutes.
If I may ask a question, when does the reviewer present or ask questions, if at all?
So the reviewer has a chance to ask the opponent and the reporter after the concluding remark of the opposition.
Got it. And how long does that last?
I believe that lasts 3 minutes.
Okay.
Is there also a reviewer presentation?
Yes.
And when does that occur? That occurs after the reviewer questioning?
So reviewer questions, then they get a bit of time to prepare, and then afterwards they go on stage. Yes.
Great, thanks.
Yeah, you can find the detailed time in the rules and regulations. we please get the opponent ready to share their slides, please? All right, opponent, are you ready?
Yeah, can you see the slides?
Yes, please go
Okay.
ahead.
My name is Selena, and I'll be opposing problem A, droplet microscope. The problem statement reads, by looking through a single water droplet placed on a glass surface, one can observe that the droplet acts as an imaging system. Investigate the magnification and resolution of such a lens. So for a summary of the reporter characterized the droplet using Young's equation. The reporter discussed how light refracts using a modified thin lens equation. And then the reporter then derived a formula for the magnification of the drop. Their setup consists of a DSLR camera mounted on a tripod that it images known pixel sizes and a resolution test target to measure both magnification and resolution. And they were able to obtain data varying like drop volume and the drop itself. As for merits of the report on the theoretical side, the report explained why the drop magnifies an image. They quantified refraction and the magnification of the system. They characterized the droplet to using a SSL drop model and the Young-Laplace equation, and then also solved a set of differential equations numerically to obtain the entire shape of the drop. Experimentally, they were able to measure resolution and magnification by imaging different printed images and accounted for the evaporation of the drops, which is very commendable. They accounted for the focus of the camera and then for some concerns and improvement suggestions. On the theoretical side, there was no explanation as to why the resolution changes physically, which we can talk more about in the discussion. Additionally, it's unclear as to how the shape of the drop connects to the objects of the system, which we can clarify further in the discussion. So a suggestion for this is in order to connect the shape of the drop that you obtain using the Young-Laplace equation, you can instead trace rays from the camera and refract the rays according to Snell's law using this shape of the drop, and therefore you can produce an image, and this would capture the full extent of the phenomenon. On the experimental side, so the use of a USAF 1951 resolution target test measures a combination of both contrast and resolution, since the ability to distinguish a line pair depends on both the contrast and resolution of the photo, because the imaging system will change both the resolution and contrast of the image. Additionally, the resolution depends on the distance between the camera and the object plane. The focus plane is not specified, so a decreased focus on the object plane would lower the resolution of the image because the blur would on the image would prevent the ability to distinguish a line pair. So as for improvement suggestions, we would suggest taking contrast measurements at different varying distances from the object to the camera. And this way we can obtain contrast as a function of resolution for a more generalized way and consistent way to quantify resolution and And then additionally, we also suggest to use a higher f-stop or a smaller aperture size on your DSLR camera. And this way you allow in less light and increase the depth of field, and therefore the entire image can be in focus, and the image will then be sharper. And additionally, we also suggest using perhaps a lower ISO and a lower shutter speed for better contrast in the image, and overall this would increase the resolution of your system and provide more accurate measurements. So at this time, I would like to invite the opponent up for a discussion.
Thank you. So do you want me to share my slides?
Yeah, could you share slides?
Can you see this?
Could you give me a second?
Yeah, we can.
Okay, so to start, could you quickly explain where the change in resolution comes from in your imaging system?
So I think the change in resolution just comes from the slightly different magnification based on the droplet size. So like based on what we have here, this is where the change in resolution comes in.
But why is resolution different? Like, why do you see like a more blurred image?
We didn't see a more blurred image. The line pairs that we identified were just slightly different.
But like, why are you unable to physically? Why does this change in resolution happen?
I'm not too sure.
Okay, so we believe that the change in resolution comes from like a variety of factors, such as like chromatic aberration, spherical aberration, and scattering, which would cause like some kinds of blurring in the image, and therefore it'd be difficult to distinguish like line pairs. And so we believe that like this wasn't accounted for in like both the experiment and the theory. And so perhaps you could have instead of using formulas to calculate like the resolution like numerically, instead you could like obtain the actual image like itself. But we can talk about that later. That's okay.
Okay.
On the topic of resolution, I want to ask like, what happens to the resolution as you like move your camera away from the target?
The resolution should decrease because you're moving it out of the focal. Like the resolution, like I don't think you would be able to accurately measure it because it would be out of focus.
So, wait, could you repeat? Like, what do you mean by that?
The focal length wouldn't match. Like as you move it away, you're changing how far the droplet is. Like you're talking about moving the droplet away from the target.
Moving the camera away from like the droplet, yeah.
Oh yeah.
Like,
okay. I think it's essentially the same, but I think that it would go out of focus. So I think you wouldn't be able to measure it if you did move it. Because
I would like disagree. I think that the resolution would like decrease as you move away from the target, which is why like I find it great that you kept the height consistent in your trials, because like because the further you are away, there are fewer like pixels per inch, and this way your resolution would decrease. And that's why like as we suggested, like it'd be better to image the line pairs at different heights, and that way you can obtain like the full scope of the resolution measurements.
Okay.
But that's okay.
Like in our thing, if we moved it away, like it would be out of focus. We wouldn't get any validity. Because we were using really small droplets, so that may have been something that was different.
Okay. Could you go to the slide with your droplet like 28, I think? Here when you're measuring, are these your like own like data points?
No, some of these were from other research that we was in. Oh.
Okay. But for magnification here, would you agree that magnification is not constant throughout your drop? Like different.
Sorry, my computer just died.
Oh, that's okay.
Sorry. Could you repeat that?
Would you agree that magnification is different like across the drop? Like it changes as you go further from the center of the drop?
Yeah, I do agree.
So here in your graph of magnification versus volume, where in the drop are you measuring?
We're looking at the center.
Okay. And so as your volume increases, what would you think the magnification like would go to? Like say you had like an infinitely large drop. What would what would the magnification of that drop be?
I don't think there would be any magnification if the drop was infinitely large, because it would just act as like more slides.
Sorry, are you still sharing your screen?
My computer is dead, and I don't have my slides on my other computer. Hold on, I'll try to find a copy.
Okay, that's okay. But I partially agree with that. Like I agree that magnification would like sort of asymptote to 1, but like if your camera was placed close to your image, I believe that there would still be some sort of magnification because the rays, if the rays you're sending out from the camera would not be parallel, and therefore when you're sending out an amount of rays, the distance between the rays on the object plane would be greater, and therefore there would still be some sort of magnification in your system. But that's okay. We can move on. So could you explain, I know you don't have your slide now, but could you explain briefly how you connect your drop shape or your solution of the SSL drop to your optics?
Yeah, so essentially we were able to model the drop in MATLAB, and then using that we were we modeled the magnification and resolution using the droplet that we simulated.
Do you have any images or visuals on your drop shape that it outputted?
Yeah, I did, but now they're I did, but then those slides got removed because I didn't save. So I'm sorry, I don't have them here right now.
Okay, that's okay. When you were solving these equations, for an increasing drop size, did the contact angle change?
Yeah, it did change. But the change. Sorry, yeah.
But in an earlier slide, I think you mentioned that the contact angle was as a function of the surface tension between the drop and the air, and also the drop and the substrate. So, did you account for the constant pinned angle? Because if your angle is changing, then your theory doesn't agree with.
Well, when we changed the angle, we also changed the profile of the droplet, so the magnification would increase or decrease because the curvature changes.
Wait, sorry. What I meant was in your theory, you mentioned somewhere that the contact angle is constant for a given type drop liquid and substrate. But you also mentioned that the contact angle changes with volume.
I don't think I mentioned that the contact angle stays constant, but contact angle was one of the variables that we were measuring.
Okay, I would like to disagree with that because I believe that contact angle should stay constant for given materials. But that's okay. Could you explain now, moving on to the optics part of your theory, why you used a double lens equation and what the lenses are in your system?
So we use a double lens equation because we believe that the droplet acts as a thick lens because we think that it's enough for it to be considered that the image reflects from the interface between the glass and the droplet, and then the droplet and the air medium. So that's why we use a double lens.
But the glass is a flat surface. Do you account for that as well?
Okay, yeah, but like you mentioned earlier, even when the droplet is infinitely large, there's still the flat surface will still cause a slight magnification. So that's why we did consider that.
But when your camera is sufficiently far away, which from your images it is, there should be pretty much no magnification caused by a flat.
Okay, our camera was actually much closer in the experiments. So we did think that it was important to consider, but I do think that you are right that when the camera is far away, that it wouldn't be as important to consider.
Okay. One last thing. Could you go? Oh, sorry, you don't have the slides, but could you explain how you solve the set of differential equations that you showed?
We had code for it, but essentially we just it was provided from a one of the papers that we cited. So we used their solution to solve the droplet profile.
Okay, so did that output the entire profile of the drop? Were you able to obtain the entire shape of the drop?
Yeah.
So why did those equations not apply to Okay, so, sorry. Like physically, like what would the drop shape look like as volume increases?
The droplet, the drop shape, so it would become less and less of a spherical drop and more of a like the concavity would decrease. Sorry, the convexity would decrease essentially.
Right, I would agree with that because like gravity would have like a stronger impact on the drop because with a greater volume. I think our time is up.
Right, that's all we have time for. So we'll move on to the next stage, which is the opposition summary.
Okay, so I'd like to first of all thank the reporter for their report. So first, we discussed quickly the change in resolution and how like why the optical system would result in a change in resolution. And the reporter did not really discuss this in their report, even though it's like one of the key parts of the like problem statement. But I added that it was because of like aberration or scattering in the system. Then we talked a bit about the parameters that the reporter varied. So we talked about like how magnification was not constant across the drop. So we clarified that the magnification measurements were at the center. And we also, the reporter correctly like identified that the magnification will asymptote. However, they did not like realize that the magnification will not asymptote to 1 exactly if like the drop is flat because they use the camera. Okay, thank you.
All right, thank you. We'll move to the next stage in which we have questions from the reviewer.
Can everyone hear me?
Yep.
Okay, so question for the reporter. I have a question about how you counted hydrophobicity of the surface in your presentation, because as I found in my findings, the hydrophobicity of the glass slide is very important to the formation of the water droplet and magnification. Can you clarify that, please?
Yeah, so that was actually one of our future works. We weren't able to classify the hydrophobicity because of our limited resources, but that's something we would like to do in the future.
Okay, I see. A question for the opposition. You mentioned that you believe that the contact angle is constant for a surface, for a given surface. Is that correct?
Right, yeah, that's correct.
And so how do you think that volume affects the the contact angle of the water droplet on the surface?
So for like a constant like liquid and substrate, the contact angle will not change with changing volume, and this is known in literature.
So you're saying that regardless of the volume of water, if it's the same substrate and same surface, it will have the exact same contact angle?
Right, yeah. Yes.
So my question to you then is, if I take a water droplet that is 1 microliter in volume, and I take a water droplet that is 1 liter in volume, how will their contact angle change if on a droplet on the same exact surface?
The contact angle will be the same, but the shape of the droplet will be different. Like the curvature away from like the contact will be different, but the contact angle itself will be the same.
I believe that the contact angle will be the same. Okay. Question for the presenter. I saw that your resolution did not change at all. Can you please explain more why in your theory the resolution would change, but in your data the resolution did not change?
Yeah, so in our data, like we mentioned, since we were using such small droplets and the variance in such small droplets is really small, and that's why we saw barely any resolution change. We did see there was a slight increase, but we do believe that as we increase the size of the droplets, the resolution would increase.
And why would that be?
We think that it's because it's bigger, so there's like the focal length is there's a greater there's a greater I guess area area where you can place the camera with a where the focal length is able to give you an accurate resolution.
Sorry, on slide 4 of your presentation, your diagram showed that the lens is a convex lens where the rays radiate out. But if the image is behind the lens, would the rays not be kind of converged to your imaging system?
Yeah, they would be. That diagram was made really. Sorry, that diagram was made really quickly because the diagram that we used to have wasn't there anymore.
So you're saying that the
time
diagram,
for.
Yeah, I agree with you.
Yeah. So we'll move to the next stage, preparation of the reviewer.
Yep.
Reviewer, please get ready to share your slides.
I'm ready to go.
Yeah, please go ahead.
Sorry, can I have time to open my presentation?
Yeah, please go ahead. Yeah.
Can everybody see my screen?
Yes, we can see your screen.
Okay, so beginning my review. So I'm going to restate the problem statement. So by looking through a single water droplet placed on a glass surface, one can observe that the droplet acts as an imaging system, investigate the magnification and resolution of such a lens. Okay, so the tasks for this problem were creating a reliable and accurate experimental setup, which they did, qualitatively explain the phenomenon, which they missed for resolution, I believe, investigate the key parameters, predict the magnification and resolution using theoretical models, and demonstrate that the predictions sufficiently match the data observed, and analyze the impact of each identified key parameters on the trends. So summary of the report. First, they talked about droplet profiling, then they talked about a refractive analysis, and finally, how they calculated the resolution. And then they spoke about, for experimentally, they confirmed it with the magnification, the droplet substance and volume, and then resolution. Now, here is the reporter merits and possible next steps. I think that their experiment was well done, and using the U.S. Air Force resolution test was well done. The theory was very extensive. I think that the droplet profile and refractive analysis and optical resolution and index analysis was well done. I think for possible next steps, they should look into varying surface hydrophobicity of the glass slide itself, looking into expanding the range of data for the model, so making water droplets of, 10, 20, 30, 40, 50 microliters in that area, looking into exploring resolution more deeply and understanding how it actually works qualitatively, and modeling the water droplet as a lens. So I'm looking at how the glass block or slide affects the properties of the question and exploring ray refraction, as they missed on slide 4. So summary of the opposition argument. They asked more about the resolution and how different parameters and measuring techniques affected the resolution, the connection between the optics and shape of the droplet, and how magnification varies throughout the droplet. These were the main points raised. So for the opponent, I think that exploring the experimental setup of the presentation was very well done. That's a valid point in my opinion. It was also a well done summary of the reporter's report, and pointing out the inconsistencies in resolution was also accurate in my opinion. I would ask that the opponent looked more into the geometrical models of the reporter, specifically on slide 4, and looking how the ray refraction actually occurs, discussing more about the refractive properties of the glass surfaces and whether it was taken accounted for in the theory, so the glass slide itself, and reviewing how water volume actually affects contact angle, from which we discussed in the question period. So the discussion and analysis. First, they opened with resolution. There were some questions. The opponent asked how resolution changed and why, and the reporter said that they had not measured it and they don't exactly know why as you move away from the imaging system. In my opinion, the point raised by the opponent that chromatic aberration is significant to resolution is incorrect, because at those volumes of water and at the physical size of the lens, chromatic aberration just doesn't have the time to actually occur. And in my empirical data, I didn't notice at any chromatic aberration occurring. And I also disagree with the reporter's response that the resolution does not change as the imaging system moves away. Now, the next question, or the next point, was magnification throughout the droplet. So the opponent correctly said that magnification is not constant throughout the drop, and the reporter replied that they only measured through the center of the drop. And I agree that the magnification is different across the different parts of the water droplet, because the curvature is different at different points. And I think that the possible next step could be looking into the magnification at these different points. As for contact angle, the opponent raised a point about how contact angle changes by changing volume. The opponent said that contact angle does not change at all, regardless of volume, assuming a constant surface of the same type and the same substrate.
We're out of time.
Okay.
So we'll move on to the next.
Can I finish my general suggestions? I can make it in 10 seconds.
Sure.
Okay, I would suggest that expanding more on the parameters of the question, looking into hydrophobicity and larger water droplet volume, looking at the refraction of the glass plate, and looking more into why resolution changes. That's it.
Thanks. So next stage, concluding remark of the reporter.
Yeah, so today we discussed problem B, droplet microscope. So first, I went over a report of our findings of the problem, including a repeatable experimental setup, theoretical models for the droplet, the magnification, and the resolution. And then we looked at some key correlations between relevant parameters. And then I had a discussion with the opponent where we went over our experimental setup, so camera settings in particular, and also the distance of our camera. And we also discussed, clarified some clarified how we model the water droplet itself. And we also discussed some, I believe, key significances in the different variables of contact angle, how the droplet would behave as it became infinitely large, magnification, and how we can improve our resolution model. And after that, the reviewer summarized everything that we mentioned today, and made points on future improvements, which we thought were good. And they also agreed and disagreed with the statements that we made, with good explanations. And as well mentioned how we can make a better report altogether in the future. So overall, I believe we had a fruitful discussion today, and that there was a lot to take away. And yeah, thank you.
All right, let's move to the next stage of jury questions. 5 minutes. Anyone would like to ask a question? First.
Perhaps I can get started. So I have one for the reporter. I don't think you have the slides anymore, but we're talking about the sort of E naught term, right? This number that you mentioned at the very beginning.
Yeah.
So could you just outline how the shape changes when E naught, between E naught less than 1 and E naught bigger than 1? Could you sort of identify these two regimes? So I'm assuming something, changes when you change the regime.
Yeah, so when it's less than 1, we believe that the shape would be more circular because it's more surface tension based, so there would be a more equal distribution of how the droplet is formed, while if it's greater than 1, we think that it would be like flatter at the top and less convex because gravity takes over, and so therefore when there's more substance in the middle of the droplet, it would be less convex.
Okay, thank you.
Any other questions? More questions? Last call for questions from jurors. Not, then we will move on to grading then. I think the jurors are treating the teams pretty well. Obviously, if you don't give an answer, there is no chance that you can lose a mark at the end, so that's good.
Sorry, who were the questions for? Oh no, sorry, this is the grading
No,
period.
it's done. It's done. You're all good.
Yeah. My apologies.
Right. Yeah. So when you're done with grading, please just upload and maybe send me a message in Zoom so I know. After I receive everyone's grades, we can move on to our break.
Oh, and once again, do you think we can go over the problems and the teams?
Right. So the problems. So for next stage, UTS Shroomsky is the reporter. They're reporting magnetic here. Team UTS 5 is the opponent. And then team affiliated is the reviewer.
Okay, wonderful. Thanks.
So after the third stage, I would just like to ask everyone if you're staying for the closing/reward plus award ceremony, you can just stay in this Zoom room for another 15 or 20 minutes. We should be able to get the scores all calculated, and then we will go to the award ceremony. That's good. I have the scores from most of the jurors. Except maybe 2. All right. Well, I got the scores from everyone. So then we can go to a break for perhaps this time we could do a little bit shorter, like still about maybe 5 minutes. And then we'll come back at 6:15 p.m. EST. I just want to check, Jerry, are you ready to take over as timer? All right.
Yeah.
Sounds good. All right. Hi, everyone. Welcome back. This will be the third and final stage of the Canadian Young Physicists Tournament 2024 final physics match. So we have the reporting team being Team UTS Shroomskis, the opposition team being UTS 5, and the reviewing team being Team Affiliated. Let's just check if all the teams are here. Shroomskis, are you there? Team Affiliated, are you there?
We are here. Wait, does my working?
Yes, we can hear you. And then is UTS 5 there?
UTS 5 is present.
All right. And Jerry, we could just set up the timer. And we made a bit of a technical change because we realized that when we're streaming it, when we're sharing both the clock and the slides using screen sharing, the stream is only seeing the clock. So that's why we changed the clock to essentially one of the volunteering accounts, their like video feed. So you can take a look at it over there. All right, that being said, I think we can get started. So the problem that the reporting team will be presenting is magnetic gear. Let's start the 5 minutes preparation. Right, reporter, are you ready to start?
Yep, I'm ready.
Please begin.
All right. Hi, I'm Nathan from Team UTS Shrimskis, and today I'll be reporting problem G, magnetic gear. The problem statement tells us to take several identical fidget spinners and attach magnets to their ends. When placed side by side on a plane when one is rotated, the remaining magnets may rotate only due to the magnetic field. We're to investigate and explain this phenomenon. So now for an overview of here's an overview of my presentation. We'll begin with the phenomenon. Our experimental setup consists of 3D printed spinners, which have spaces for neodymium magnets on their ends, and these spinners are able to spin differently. And so in order to have precise control over the motion of our driving spinner, we'll motorize our spinner by using a gear and chain and attaching it to a stepper motor. And so the simplest case of our phenomenon is when the circumferences of our spinners overlap. And so in this case, the driven spinner perfectly drives the other spinner like a normal gear due to the repulsion between magnets. However, this case is trivial and will not be investigated further in this report. So now, if we separate the spinners a little bit, let's see what happens at various driving frequencies. So at no driving frequency, the free gear will experience small oscillations when it's disrupted from its equilibrium. Try the video. Okay. At a slightly greater driving frequency, we can observe small oscillations which grow and evolve over time. However, the free gear does not counter-rotate and just oscillates back and forth. And so if we further increase our driving frequency, the free gear may begin to counter-rotate irregularly closer to the behavior of a real gear. Sorry, the videos are a bit laggy. At a very high driving frequency, the free gear may experience small oscillations. So now let's explore the two simplest cases, no driving frequency and a very high driving frequency. We can track the angle of the spinners over time to visualize the trajectories and then perform a fast Fourier transform on these trajectories to notice that for the fixed gear case, there's a single slow frequency, while for the high omega case, we see a slow frequency as well as a peak at 4 times the driving frequency, which is like frequency that of each arm coming around. And so for a qualitative explanation of our phenomenon, we'll note that when all of our magnets are aligned in the same direction, they will repel. So then we'll first explain the case where one gear is fixed. We note that due to the character of our magnetic force, the interaction region of all of our magnets is only within a small radius from their centers. And so when the free gear is disturbed from its equilibrium, it will experience a force that drives it backwards, and the same thing for the other arm. Thus, the free gear can oscillate at a natural frequency dependent on the spinner inertia and the magnetic field. And so now if we increase our driving frequency, if we increase our angular velocity of the driven gear, we can notice small oscillations but no counter rotation. And we can explain this by examining how the free gear can oscillate around each arm of the driven gear. But since energy is being both added and removed by the driven gear, there's no net transfer of energy. And so now if we increase our angular velocity even more, we can occasionally see periodic driving of the free gear. And so in an ideal case, the driven gear only adds energy by only being in the interaction zone of the incoming side of the driven gear. However, in order for this state to be stable, the amount of energy input must match the amount of energy lost due to damping. However, in reality, our free gear will often accelerate out of this stable state, as shown in the video. So at very high driving frequencies, we see small oscillations again. And so since the free gear's magnets are being accelerated and decelerated by the same amount, by the driven gear, there's no net gain in energy. And so the slow frequency that we observed on the FFT can be thought of as the free gear oscillating in and out of the interaction zone of the entire driven gear, since it is spinning at a very high frequency. And so if we want our gear to act like an actual gear, we can try driving our spinner at a constant acceleration. And this way our gear keep up with the free gear as it accelerates. So now on to the first component of our theoretical model, magnetics. So we can, a simple model for our permanent magnets might be an ideal dipole model, which treats our magnets as tiny rings of current with their own magnetic moment. And so there's a known relationship for the force between two dipoles along the same axis. However, in our case, since our magnets are coplanar, the force between two ideal dipoles is 0. And so in order to model the force between our magnets, we must then consider the finite volume of our cylinders. And so to do this, we'll determine the B field outside of our magnet by determining the H field, defined as follows, by the use of a magnetic scalar potential. And so the use of our scalar potential is valid because of the lack of free currents and the fact that our magnet is uniformly magnetized. And so to determine this scalar potential around our magnet, we'll integrate the contribution due to the sources of the H field on the poles of the magnet. And this integration is done by summing the contributions of the upper and lower sources of our H field. And so this computation is performed with the use of elliptical integrals to determine the B field around our permanent magnet. And so now that we know the field away from our magnet, we can determine the force by discretizing our magnet and using the known equation for the force on a dipole and integrating this force over every volume element on the magnet. And so if we plot the force between our magnets as a function of distance, we can see that the force drops off quite quickly with distance. In that when we plot on a log-log scale, we show that we can see that the force is highly nonlinear with small separations. So now onto modeling the dynamics of our gears. So we define the geometry of our spinner as shown, as well as the position of each magnet on our spinner. We can expand this to include a second spinner and determine the distance between any pair of magnets. So to determine the torque due to the magnetic force, we can sum the tangential components of each force on all of our magnets and then use Newton's second law for rotation to determine the acceleration of our spinner in every time step. So since there's only a small interaction range of each of our magnets, we'll only consider the force in a small radius away from each magnet. So we also include damping by attributing our energy loss to two primary sources, linear air resistance and constant friction. And so we can add these torques to our equation of motion and solve this ODE numerically with RK4. So here's the result of our simulation. We can simulate the motion of our spinners and compare it with our theory. So now finally, we'll go on to our experiments. So to begin, we'll start by characterizing physical parameters in the system. Firstly, to characterize our magnet, we'll direct a magnetic field probe at a neodymium magnet whose distance from the probe can be varied with an adjustable lab jack. We can fit the field away from the magnet using our theory from the magnetic section to determine the magnetization of our neodymium. Next, to characterize moment of inertia, we use the method of bifilar suspension, where we allow our spinner to torsionally oscillate, and then we can equate motion for the twist angle of our spinner and measure the frequency at various lengths, and then fit our theory to determine our spinner's moment of inertia. Next, to characterize damping, we simply allow our spinner to decelerate and then fit the decay of our spin due to friction and air resistance. So now we'll verify our trajectory for various cases. So first, for the simple case of the fixed gear, we can compare our theory and experiment. And we can observe good comparison between our theoretical simulation and our track data. So now plotting the trajectory of our free gear, where the driven gear has a low angular velocity, we again see good comparison between our theory and experiment and our simulation results, And then if we further increase our angular velocity, we see fairly good we see in our theory predicts a decrease in the amplitude of oscillation towards a stable state. However, our experiments show this decrease, but instead of remaining in the stable state, the spinner exits and the amplitude increases. And this is because our angular velocity is not perfectly constant and the phase of our spinner may deviate for each period. But still, to verify that our theory predicts the frequencies, we perform an FFT on our theory and experiment and see good prediction of the slow frequency and the driving frequency. Lastly, it is also important to note that the frequency ratio between the slow and driving frequency is roughly 4. And later we'll explore why this ratio must always be an integer in order to see stability. So now we'll compare our theory and experiment for the constant acceleration case, and unsurprisingly, we see that the free gear is driven at constant acceleration of the driven gear. So now we'll explore the mechanism of energy transfer and understand why we can observe stable configurations. So if we run our simulation for various driving frequencies and plot the angular distance spun after like 10 seconds, we can see the following trend. And both theoretically and experimentally, we see both stable and chaotic regions. So let's try to get a better understanding of why we can observe stability with this constant velocity. So remember from our qualitative explanation that the motion of our spinner is determined by the energy transfer and removal due to the driven spinner. So we can write the power transfer to the free spinner as the product of torque and velocity, and then as it's graphed there. And then we can integrate the power over time to give us the net work done on this free spinner due to the driven spinner. And so we notice in this stable configuration, the overall work done through each period is 0. And so then this configuration is therefore stable because the spinner is going slow enough that any added energy can be removed by damping, allowing the phase to regulate itself to be equal after each period, resulting in the stable configuration that you can see here. And so when we plot the same graphs for high angular velocity, we notice a similar pattern. Again, while the system does begin a bit chaotic, then it reaches a stable configuration where the power inputted matches the power extracted. And so this stable configuration requires the slower frequency to be an integer multiple of the the fast frequency in order for the phase to be equal at each period, because you want the phase to be equal when as the driving spinner comes around each time. So now for constant acceleration, we can plot the gear driving ratio for various driving accelerations. And this is basically a measure of how many rotations the free gear makes for every one rotation of the driven gear. And we can see that at small driving accelerations, the system begins chaotic. At higher driving accelerations, we see one-to-one driving, so like a real gear. And then when the acceleration is too high, we do not see any driving. So again, plotting the work done on the free gear, we notice that it again starts a bit chaotic, but eventually finds stability, this time with energy increasing steadily over time, meaning the energy inputted will always be greater than the energy extracted through each cycle, as previously explained in our qualitative. So lastly, we'll vary a few parameters. So firstly, varying the separation of our two magnets. Video is not playing. A good way to get insight into the primary changes of these parameters will compare the FFTs of our trajectory and note that increasing the separation causes the driving frequency peak to become more dominant, which is because the slower frequency is weakened due to the interaction zone being weaker, and we can still see this periodic driving. A similar trend occurs when we reduce the magnet strength. Again, this weaker interaction zone results in the driving frequency becoming the dominating frequency in our domain. Now we can vary arm count, and the primary result that we observe is that the driving frequency is a factor of 3 instead of 4, and that the amplitude of the slow frequency decreases since the angle between the spinners has increased. And lastly, if we change the arm count from 4 to 3, and as shown here, we vary the arm length from short to long, shown here. The length between this, we see the slow frequency becomes far lower and barely observable in our experiment. All right. Lastly, for a quick brief look into further insights, we noticed that when using constant acceleration, there was high variation in our acceleration, in our whether or not our free gear is driven. So if we run our simulation for various driving accelerations, we can see we can observe regions of cutoff points where we can observe one-to-one driving and points where we do not observe one-to-one driving. So this shows us that predicting whether or not our gears are driving is complex but deterministic and highly dependent on the phase of our spinners. In summary,
that is all we have time for. So we'll move on to the next stage, which is opponents' questions.
Great. So first, thank you for such an amazing presentation. Just a few questions around your presentation. So one question is how did you control the velocity of the spinners?
So the velocity of the spinners is controlled by using a stepper motor, which rotates the same number of steps for each time step. So therefore, the velocity is able to be consistently controlled.
Okay. Second question, did you measure the magnets with the Gauss meter?
Yes, the field away from the magnets is probed at various distances using the Gauss meter in our magnet characterization.
Great. Thirdly, in terms of your gear models, how did you consider the radius of the forces of for the magnets?
Pardon? What do you mean by radius of the forces?
Like the radius of the magnetic forces analyzed in your presentation. How are you able to consider that how are you able to measure that for magnets?
Right. So in each time step, our simulation calculates the separation between each pair of two magnets, and then we use our magnetics model to determine the force between the magnets due to at this specific separation.
Okay. So if you go to one of your slides, I think it was the slides 44, I think, there was this big discrepancy between your theoretical and your quantitative data. Could you explain that discrepancy and why there was so much error within the theoretical model?
Right. So as I explained, when I discussed energy transfer, it requires the phase to be perfectly equal after every cycle. And so in our experiment, the velocity may not always be perfectly constant, and there may be slight perturbations. So it's very easy for an experiment for the gear to exit this sort of stable state, while in our theory, there is no perturbations added, so it will always remain in the steady state.
Okay, thank you.
Thank you.
I believe that's time.
Yeah, 3 minutes of preparation of the opponent. So next stage is opponent takes the stage. You may begin whenever you're ready.
Okay. Okay, sorry. I need a bit of. Okay, great. So hello everyone, my name is Daniel from UTS-5. I'm here to present question G, magnetic gear. So the problem statement states if you take several identical fidget spinners and attach neodymium magnets to their ends, if you place them side by side on a plane and rotate one of them, the remaining ones will start to rotate due to the magnetic field. Investigate and explain this phenomenon. So you'll hear the tasks listed out that should be completed by the reporter. Task 1 is to create a reliable and accurate experimental setup. Task 2 is to qualitatively explain the phenomenon. Task 3 to investigate the key parameters. Task 4 to predict relevant parameters using theoretical models. Task 5 to demonstrate the predictions sufficiently match the data observed. And lastly, to analyze the impact of each identified key parameters and their trend. So here's some summary of the report that Nathan excellently executed. So firstly, they have their amazing theory on magnetics, an ideal dipole model, and their dynamic gear dynamics. And secondly, they have their experiments with 3D printed gears driven by a belt with controlled speeds. And lastly, they have the parameters and trend analysis, including separation, magnetic strength, and arm count. So here are some merits and next steps that they should consider. One, on the merits, we believe it's a very thorough experiment accounting for the torques, air resistance, etc. Secondly, excellent qualitative analysis of the phenomenon and theory experimental findings match. Some possible next steps we should consider is that one, the moment of inertia calculation could be improved. Secondly, there should be more exploration around how forces affecting the spinners should be minimized. For example, the friction the spinners spinners experience internally, and also we suggest that because they use chains for experiments, chains are usually quite slack, and I would suggest using a belt inside for tighter tensions and therefore more accurate measurements of angular velocity. And thirdly, just on the theory and have easier to read formulas. So overview of discussion, we say that there should be discussions around the experimental verification, especially on one of their slides when their theory did not match with their data. Secondly, on the moment of inertia calculations. Thirdly, on the experimental setup, including, as I mentioned before, the belt maybe replacing the chains with a belt for more controlled angular velocity. And lastly, on the discrepancies between model and data and how that could be improved next time. Thank you.
Please advance the clock. Yes.
Okay. Great. So now going to the questioning period. Nathan, could you share your slides again, please?
Yes. Could be sharing.
Okay, yes, great. So if you go to one of the slides with your a picture of your experimental setup, did you account for friction within your experimental setup? For example, the friction within the pivot points in the center, and did you take any measures to reduce it?
Yes. So the friction within the bearings of the spinners is accounted for in it is treated sort of as a constant damping. So that is considered in our theory. As for experimental ways to decrease this, we could possibly reduce the friction by adding a lubricant or something. However, our friction is accounted for in our theory.
Okay, great. And secondly, wouldn't you agree that if you replace the chains with belts, that could increase the angular velocity, that more accurately control the angular, the rotation for the fidget spinners? Because
I don't think I would fully agree, because I think the belt doesn't, or sorry, the chain doesn't slip along the prongs of our 3D printed physical gears. So and in the actual experiment, stepper motor is like pulled taut so that it's not slack and there's no slipping. So I think we're able to get pretty constant angular velocities. Although perhaps I could try using a belt, but I think the chain works pretty well.
Okay. I might disagree considering the chains are quite slack and they lack tension within them. So maybe you can consider tighter tensions next time. But moving on, so how would you consider improving the energy efficiency of the setup next time to better match the qualitative model?
What do you mean by that?
Like considering there are some effects caused by dampening and also some discrepancies within the data and the theoretical model, how would you improve that next time?
Oh, so I think to improve that, that's mostly mostly about like focusing on improving the experiment and making sure that like the angular velocity is like actually perfectly constant, and like perhaps like making sure that there is no like slight perturbations, that like the actual bearing is like it's like perfectly like lubricated, because sometimes it can like stick a little bit, which causes this deviation, and the phase match can be like offset. So possibly due to that, or I think the theory experiment right now is well explained.
Also, does your like model or theoretical model account for the length of the spinner arms?
Yes, so it does account for the separation between the center and the magnet, or the distance between the center and the magnet. And
could you
that
give us a slide that's where your theoretical model accounted for that? Okay, great.
Oh, sorry, not this one. Here's a comparison with varying the arm length. So the top one is using a short arm, and the bottom is using a long arm.
So what would the result be when you vary the arm length? Would the trend be on the dependent parameters?
So when we increased arm length, we noticed that like the arc length between like the two magnets is really increased. So as when we discussed in our qualitative, like the small oscillations, like the slow frequency, that's dependent on like the free gear oscillating like through the like along this arc length. So when this arc length becomes a lot bigger, the slow frequency becomes a lot smaller, and we also and so this is observed both theoretically and experimentally, as shown here.
Okay, great. So another question would be that does your theoretical model account for the distance between spinners quantitatively, or is it just qualitative explanation?
It does quantitatively account for the distance between spinners, and this was also theoretically and experimentally.
Okay, great. And also, okay, so is the blue line in your graph the theoretical models?
Oh, right. Sorry. Yes. Like it's the same color scheme as before, where the blue line represents the theory and the red represents the experiment.
So could you explain some discrepancies between the theoretical and the like during the very high peaks of the theoretical and high peaks of the experimental data? Why were sometimes it was higher and sometimes it was lower in the discrepancies? How can you explain that next?
A big discrepancy is like in the top graph, where like the driving frequency is the experimental driving frequency is like really over predicted by our theory, and that's because often the free gear like is able to escape the stable state, and also due to the fact that these oscillations are really small, and so tracking them can sometimes be difficult. So experimentally, this frequency is not as dominant in our like frequency domain because firstly, due to like the fact that they're small and hard to track, and secondly, due to the fact that the spinners escape the stable state, where that frequency is most prevalent.
Do you think another question would be that you track the location and the other variables of, for example, angular velocity of the spinner within tracker? Do you think because oftentimes you have to hand track the locations within tracker? So how do that contribute to the discrepancies within your model, and how do you improve that next time?
I did not use hand tracking. Like it's all auto track.
So everything's auto tracked?
Yes.
Okay, great. So also another question is that was your angular velocity rotation completely constant within each of the experiment done, or was there any discrepancies within the speed of rotation?
The assumption is that it is constant. However, there are of course deviations in our angular velocity. the stepper motor may not perfectly be able to like spin at a constant speed, especially because the magnets on the other spinner cause like high repulsion forces. However, like we make the assumption that it is constant.
Okay. Last question is that do you think the moment of inertia of your calculation is accurate since you're accounting for the ball bearing, but I believe in the actual experiment, the center of the ball bearing are not spinning with the spinner?
So in our characterization, we only characterize a 3D printed spinner, and so the ball bearing like since the ball bearing is really close to the center, the contribution to the moment of inertia is small. So like this is and also like the like it is rotating like in the same way that it would rotate. And then to account for like the magnets, we use the parallel axis theorem and include the contribution of the magnets to the moment of inertia. That's what you were wondering.
Okay, great. That is all the questions I have.
All right, let's move to the concluding remark of the opponent.
All right. So to conclude off this discussion from opponent's point of view, we believe that the reporter has some excellent and very thorough experiments accounted for a lot of factors, excellent qualitative analysis, and also like thorough theory and experimental finding matches. Some possible next steps we can improve on is one, on the moment of inertia calculations, as we pointed out in my last question, of how it could be more accurate. Secondly, on the experimental setups, as in that maybe there could be more tighter tensions if you use like belts or other mechanisms and lastly on some theories and how the quantitative and the qualitative prediction theories have discrepancies that could be improved next time. So thank you, everyone.
All right, let's move on to the next stage question from the reviewer.
Oh, okay. It's good. All right. All right, ready to start. So the first question is for can you hear me? Is it? Yeah, okay.
Yes, audible. We can hear you.
All right. So the first question is for the reporter. So how do you ensure the 3D parts are tight and so no slippage happens?
What do you mean by like slippage?
Like slippage between your chains, your sprockets. I meant, sorry. Yeah.
Like there is no like slippage because the groove of the gear is quite deep, so we ensure that there is no slipping.
All right. And so how about the shaft bending with the gears and like attached to the sprockets?
The shaft does not really bend. Like the 3D print is rather rigid.
All right. So for the opponent, you mentioned how you should use the reporter should use belt instead of chains. So how does this exactly improve the system?
So if the belts could, like it wouldn't slack and you're able to make the tension tighter, which means that you're more accurately able to control the rotational motion of the spinner, which could lead to less discrepancies within the data.
And so if you were to do this, if you were to do this to experiment, how exactly would it go?
I'm sorry, what do you mean?
So if you were to do it with a belt and a sprocket, the belt instead of sprocket, how you control for the discrepancies?
So we believe that the belt, how would I control the discrepancies? We believe that the belt in of itself, having higher tension, would be able to more accurately control the rotational motion of the spinner, and we believe that that might contribute to less discrepancies. And that's my answer.
Right. And so I guess for one more thing, the reporter. So how much of a difference does this make, or if it is at all? And if so, how you fix the misalignment in your graph?
What do you mean?
Sorry, like so you know how there's misalignment in your little bit discrepancies with the theoretical and the experimental. Right. So how would how much of a difference does it make, and how would you fix this?
it does make a difference in like the shape of our trajectory, but we compared that the frequencies are predicted well. Because we perform an FFT. To improve it, we might like improve our experiment by like reducing any sort of perturbation.
All right. Robert.
There's a preparation for the reviewer. Hey viewer, please take the stage.
So can you see the screen? Yep.
Yes.
All right, so I'm gonna start. All right, so the problem was problem G, that magnetic gear. And so the question states, take several identical fidget spinners and attach neodymium magnets to their ends. If you place them side by side on a plate and rotate one of them, the remaining one starts to rotate only due to the magnetic field. Investigate and explain the phenomenon. And so for a summary of the report, by the reporter, we in the theoretical analysis, it talked about the free gear and the driven gear, some H field for magnetics, and talked about how angular velocity, acceleration, and chaos plays a role. And for the experimental verification, they talked about Fourier analysis for the frequencies and talked about parameters relating to the distance between gears, arm count, and the arm length. Right. And so for the reporter, what they did well was they had a strong qualitative understanding of the problem, and this was supported by well-drawn diagrams. And they also had a strong quantitative model with very good characterization. Their experiment setup was repeatable and accurate, and they correctly identified some key parameters. So possible next step is to experimentally control the magnetism of the gears, and to consider more tests for some variables, such as arm length, and also to minimize chaos and explain more how that plays in a role. So a little bit of a summary of the discussion. They mainly talked about to account for friction and whether to use a sprocket versus a belt, and the discrepancies of the graphs of the theoretical models and the experimental data. And so for the opponent, the merits include correctly clarified the discrepancies of the theoretical and experimental, and they identified the necessary tasks. Possible next step is to go beyond these discrepancies, and they overfocus too much on just the imperfections of the system. And so the first one of the things was discussed was what was friction considered. And so by the opponent raised how replacing belts with the replacing belts instead of sprockets should improve the angular movement of the fidget spinners. And while the reporters responded, the friction within bearings is considered, and there's constant dampening. And we agree with the reporter as the friction being accounted for by the constant dampening. But we also agree that a belt may provide a better angular movement. The next talked about how accounting for arm length, and the opponent raises how does arm length affect the problem, and the reporter responded with how as arm length increased, the slope frequency becomes a lot smaller. And so we agree with the reporter on the arm length increasing and the frequency of the slope decreasing. And finally, we talk about the discrepancies in the model versus the experimental. And so the opponent raised why is there discrepancies in such case? And the reporter responds by the energy transfers requires perfect conditions, and small perturbations and chaotic movement may cause this. And so we agree with the reporter as in our experience, we also saw chaotic movement. Yep, that's it. All right, that's it.
All right, let's move on to the next stage, which is reporters' concluding remarks.
Okay, thank you for the opposition and the review. So overall, some concerns brought up by the opponent included friction within the system, which we clarified was accounted for as an empirical constant. It was accounted for in our damping model. There was the concern that the chain may cause inaccurate angular velocities, and we clarified that our chain is tension and does not slip. However, we could lubricate the chain to prevent mechanical lockups. They brought up the arm length and distance between spinners and like the effect of these parameters, and we showed that this was predicted in our theory and shown in our slides. They did bring up the discrepancy between the FFT and the separation distance data, and I explained that the reason for this discrepancy, this over prediction of the driving frequency, was because the free gear escapes the stable state, and also because those oscillations are small, so the experimental peak is lower than the theoretical. Then they also asked if the angular velocity was constant, and I clarified that we assumed that the angular velocity is constant in our theory. However, there may be wobble due to the force of the magnets and like other imperfections in our system. But experimentally, it may not be perfect. There was also a concern about the moment of inertia calculation, and I clarified that since the ball bearing is quite close to the center, like it does not really contribute much to the moment of inertia. And then since the magnets are much heavier and further away from the center, they contribute a lot more, and they're also included in our theory. The reviewer raised a couple concerns, right? Such as the bending of the shaft and the slipping of the chain, which we clarified that chain does not slip and the shaft is printed with high density 3D print, so it does not bend. And they also suggested minimizing chaos. However, this is not possible since chaos is intrinsic to our system. So in summary, once again, we provided a qualitative explanation of the phenomenon, modeled our magnetics, explored dynamics on a simulation, and experimentally verified with parameter verification. Thank you.
All right, we can have the jury ask questions. Does anyone have any questions for any of the participants? Any questions from any jurors? Any jurors? The jurors are particularly nice today. Don't want to take any marks off from anyone. Last call. Any questions from any jurors? All right. If there are no questions, then we will just move on to the grading phase then. First, after you're done grading, please again send those score sheets to the drive, upload them into the drive, and then just let me know in chat, and then I will just tally that up, and then we will know the placement for the 3 teams that are in the finals. Feels very quiet without some questions from the jurors. There are some questions that were raised in the chat of our stream. So perhaps when the jurors finish grading, I'll relay some of these to the reporter. Still waiting on 3 score sheets. Yeah, we'll just wait for everyone's score sheets to come in, and then we will conclude this round. Yes.
So between the end of this round and the start of the announcement of the finals rankings and the award ceremony, do you know how much time there is? Like roughly?
I would estimate that since I was just calculating the scores as we go, I would estimate, I think, give me like 15 minutes. That should be enough.
Okay. And is that for the award ceremony too, or just the finals rankings?
So we will announce the ranking from the finals at the end of the award ceremony.
Okay, got it. All right, thank you.
So one more score sheet. All right, so that's all the score sheets. So that will conclude the final stage of the Canadian Young Physicists Tournament 2024 final physics match. So for all of the jurors, I thank you guys a whole lot for signing up to judge and for staying for staying with us until now. It is 7:08. And I really appreciate your help, and this tournament would not be possible without you guys. And if you want to stay and see who won, then feel free to stay. But if not, if you have anything else to do, feel free to leave. And I will calculate the scores right now. And while doing that, if the reporter is interested in knowing what the comment from chat was, someone from chat asked, "What about the eddy currents? Any thoughts on eddy currents?"
Eddy currents in like eddy currents in the magnets. I think.
Yeah. Eddy currents induced in the magnets.
I think that's probably not that important. I mean, I guess they could exist because we do use neodymium, which is conductive, but again, the volume is pretty small. So
yeah, I guess the way that you're moving it is not too fast, right?
Yeah.
So Okay. Jeffrey, you already in the room? Yeah.
Yes, I'm already here.
How was the conference?
Wait, sorry, one moment.
You guys went. Oh, okay. I guess they're busy.
All right. Hi, sorry. What's the question?
Yeah, so I was wondering how the conference.
It was very nice. Like we presented, like both you and I, we presented a lot of stuff here. He's on the other side.
That's nice.
Yeah.
That's nice.
We just finished the presentation and we are like sitting inside of the random place.
Yeah.
Right now.
Yeah. I appreciate all your help. It must have been hard to sort of juggle the conference and this.
Yeah. It was unfortunate that our presentation time was kind of during the final round. So
Right.
Yes.
So
Sorry.
yeah.
One second. Is Sakiba still here? Sure, Sakiba. Okay.
I don't think so.
Wow. The issue is that she gave some decimal scores, which is okay, which is technically it shouldn't be here, but I don't want it. But I don't want to round and cause any changes to the results. So we will keep as many decimal places as I am given, I guess.
So it's like something.
Good now. You guys have the score.
Trying to connect this.
Lots of suspense. All right. So I will relay this information to Jeffrey.
Okay, thank you. One moment. Let me get the.
Just give Jeffrey a few moments so that he could actually set up.
Yeah, Jim, can you send me the updated? Oh, okay.
Yeah, I sent it to you already in the.
Cool. One moment. Let me file that in, and we're good to go.
Yeah, just give me maybe a few seconds. Let's start maybe at like 7. Okay, let's say at 7:15. Yeah.
All right.
Cool.
Okay, is correct. Okay. Created UPS5. And what else? Now the rest. Okay. So I'm going to start. Oops, one moment. I'm not going to spoil like whatever the thing is. I don't want to spoil the thing onto the end. Okay. All right. Let me try to show it up here. The rest should be fine. Okay. Hello, you all. And now that's the end of the 8th Canadian Young Physicist Tournament 2024. And now we're at the award ceremonies to announce the results of this very exciting tournament we have this year. So, oops, it's not loading. So this
year, we have seen a lot of efforts dedicated by all the participants, the jurors, the volunteers, and everyone who's involved in the CaYPT tournament. And all this effort, sorry, can you guys hear me well? Just making sure.
We can hear you.
Okay, cool. Nice. And we sincerely appreciate all the efforts that have been devoted to this tournament this year. And now we are going to announce all the awards that have been awarded to either individuals or team. And the first individual award we have here is the Best Experiment Award. It's given to those who do the best experimental setup, whoever thinks the most, whoever thinks the most comprehensive aspects of every single part of the experiment and design the best setup for the corresponding questions. So this experiment award is given to Lu Yu Vankerwitz in UTS team, and he earns the Best Experiment Awards to recognize the most creative and effective experimental setup he has presented in front of the jurors and throughout the tournament. Congratulations to Lu Yu.
Thank you.
If it's here. Okay. All right. Do you want to say anything about your awards, Lu Yu?
Well, I just want to say thank you.
Just thank you. Okay, seems like he doesn't have a lot to talk about. So congratulate him again. And now we move on to the next one, which is the Best Theory Awards, given to the individuals who has accomplished the most thoughtful and the best theory in depth throughout the entire tournament in both day 1 and day 2. Okay, this award is given to Tom Jen in recognizing his theoretical analysis throughout the entire tournament and recognizing his efforts that devoted in his theoretical understandings. And Tom, do you want to say something about your individual accomplishment here?
First of all, I'd like to say thank you for the jurors who selected me for this award, as well as my team for helping me throughout the entire tournament. Yeah, we had a lot of stuff come up this year, but I'm glad we were still able to do well. So yeah, thank you, everyone.
Thank you, Tom. And congratulate you once again. I'll clap for you. Okay. So now there's another special awards here. It's the Asai Lari Leadership Awards. This award is named by the founder of CaYPT, and this award is given to those individuals inside of the team that present extraordinary leadership, either in making a decision, organizing a team together, or collaborating and demonstrating their collaborative spirits throughout the entire tournament. And here, we're giving out this leadership awards to Manami Otani to receive this Asai Lari Leadership Awards in recognizing the extraordinary leadership and commitment throughout the entire tournament.
So I just want to say a few things about this award in particular, because this is an award that is not nominated by us, the CaYPT committee. And so I just want to briefly talk about why this award is named after Mohammed Asai Lari. Mohammed was the founder of CaYPT, so he was actually, I think he participated in the national tournament in Iran, and then when he came to Canada to study, he co-founded our parent organization, STEM Fellowship, and then he was the first one that wanted to bring like IYPT and CaYPT, like this format of physics competition to Canada. So he's the founder of CaYPT. And we named this award to remember him because, tragically, him and also his sister Zina Asai Lari, they sadly passed away in the flight PS 752 accident a few years back. So that is why we named this award to remember him. And the reason why we have given this award to Manami is because his team only had 3 team members, and they're from the team Physics Jag, and their team leader came to us like last minute saying, we have these 3 team members, and then one member wanted to drop out, and we wanted to switch another one in. Can we do that? If we don't do that, then we'll only have 2 people that won't meet the minimum requirement for the team. And we said yes to that. And as you can see, they've finished the complete 5 selected physics matches. So I just want to commemorate his effort for bringing his team together, because it must have been challenging to work with a team that is only with 3 people and with one person switching out at the last minute. Yeah.
Yeah. Thank you, Jim, for bringing that info in. Yes, and that's a very great accomplishment from Manami. If she's here, seems like she's not here. So then I guess we'll just congratulate her for receiving this awards for the performance he had in the tournament and carrying the team throughout the tournament. Okay, so now we are finally gets to the point of the team awards for each of the team to announce their ranks, their placement, and to recognize their participation and also the efforts and commitment they have devoted to this tournament here. So the first awards here for team awards is the participation awards given to the teams. So we have Team Higgs Bozos with a total marks of 101.8. They are from school Sir Winston Churchill High School. And we recognize their commitments throughout the entire tournament. And yes. Okay. Then we're going to the next team is the Team Physics Jack. As mentioned before, it's Manami's team. They're from school St. Michael's University School, Victoria, BC, and with a total mark of 129.6. And we recognize their commitments and effort throughout the entire tournament. The next team we have for participation awards is Team UTS Subline with a total marks of 155. They are from School University of Toronto Schools, Toronto, Ontario. And we thank them for their commitments and efforts throughout the entire tournament. The next team is Team Earth to Solaris Organization with a total marks of 156 from School Oakview Trafalgar High School, Oakview, Ontario. And we thank them for their commitments throughout the entire tournament. And the next thing we have is Team We equals MC Scared with a total marks of 159.7. They are from school St. Michael's University School, Victoria, BC. And we appreciate and thank them for their commitments and effort throughout the entire tournament. And then we have Team Schrodinger Slackers with a total marks of 163.9 from Appleby College, Oakview, Ontario. And we appreciate the effort and performance throughout the entire tournament. Okay, and that's all for the participation awards. And now we're going towards the bronze medal, which are given to the teams within a certain percentage in terms of the rank. And we appreciate that the performance and also the extraordinary performance they have throughout the entire tournament. So we begin with the bronze medal with Team Swash Children with a total mark of 174. And they are a hybrid team in Toronto, Ontario, with members from different schools. And we appreciate their efforts and thank them for their commitment for the tournament and hope them have a great weekend. And the next team we have here for the bronze medal is Team Heisenbergers with a total points of 175.1. They're an independent team, not belong to any single school, and they're from Toronto, Ontario. And we appreciate what they have done and performed throughout the entire tournament and hope they have a great weekend. Okay. And the next team we have is from is Team UTS Aries with a total mark of 178.8. They are from the University of Toronto Schools, Toronto, Ontario, and we appreciate their efforts and performance throughout the entire tournament. And that's it for all the bronze medal given out, and they have performed extremely well as those teams. And now we're going to the next level, which is the silver medals. And let's begin here. So the first thing we have with the silver medal is Team UTS Bubble Guppies from University of Toronto Schools, Toronto, Ontario, with a total mark of 182.3. We appreciate the efforts, performance, and the extraordinary presentations throughout the entire tournament. So now going to the next team we have here is going to the gold medal, which are given to those who enter the finals and have competed on the same stage and performed extremely well. And we're really excited to announce the final results for the finals of who is going to win the first place. So let's begin. So the third place of the tournament is given to team affiliated with a final scores in terms of the marks they get in the finals, 42.9. And they're from Crescent School in Toronto, Ontario. They have done well in finals and they're done their best throughout the entire tournament. And we congratulate them for getting the gold medal here. But okay. Yes. And then we move on now to the, oh, sorry, one moment. Team affiliated, do you want to say anything?
Yeah, we're in a mall right now because I got kicked out of the library. We had to do the last round in the Starbucks though over there. But yeah, a lot of challenges this year, but I'm glad we were able to finish.
And thank you to all the judges and jurors and volunteers at the tournament who took their time out of their weekends to score and make sure that this could run smoothly. And also we're sorry for how the finals went because we actually didn't expect to make it. So we're sorry there was a lot of disturbances, but thank you.
You guys did great. Thank you all.
Congratulations.
Congratulations. So now we move on to our second place, given to Team UTS 5 with a final mark of 45.1. They're from University of Toronto Schools, Toronto, Ontario. And they've done extremely well in the finals and they performed well on the finals. And let's welcome UTS 5. Congrats to you guys for getting the second place in the tournament. Do you guys want to say anything?
Yeah. I would like to thank, on behalf of the team, I would like to thank our mentors, our teachers that helped us, Ms. Vanderkamp, Mr. Balkasoon, everyone that helped us, Mr. Brooks. And I'd also like to thank Archie for helping, mentoring us through this process, because as our first time competing in the competition, we were really worried about everything. We were kind of lost, but in the end, with guidance, we made it through, and we're really proud of where we got.
I'd also like to thank my wonderful teammates, Tim and Ben, for their efforts they put in. Honestly, we didn't expect to go this far, considering it's our first year in CaYPT, and we only have 3 members plus Archie helping us out. And it's a wonderful experience, and we achieved fantastic results. Thank you, everyone.
Thank you, TS5. Congratulations once again. All right, now we're going to our first place, the first place in CaYPT 2024. And it's given to Team UTS Shumsky with a final mark of 51.6 from University of Toronto Schools.
Congratulations.
Congratulations to you guys.
Congratulations, well deserved.
Yeah, you guys did really well with that presentation and throughout the entire finals. Do you guys want to say anything?
Yeah, thank you everyone, the jurors and all the volunteers who contributed to this tournament. Thank you to my teammates for being great teammates. And also thank you to we'd like to thank our supervisors, Ms. Vanderkamp, Mr. Valkasu, Mr. Brooks for their support. Yeah, thanks.
Thank you.
Thank you.
Congratulations. Congratulations.
Congratulations. So Yes,
that
you guys
sort of wraps up for our award ceremony. I'll just say a few things as sort of the organizer of this whole thing. So yeah, I would like to thank everyone for being a part of this, and I want to thank the teams for putting in several months of their work trying to solve these problems and coming on stage and present their solutions and doing discussions and talking to the jurors. And I want to thank the team leaders as well, because it is them that handle all of the administrative work to enable you guys to be able to register and compete in this fantastic tournament. And also jurors as well. As I said, this would not have been possible without the jurors. As someone that judged myself, I know that although jurors just sit there and watch your presentation, they actually have to do a lot of thinking, and it's a really tiring job. So I really appreciate all the work that you guys have put in to make sure that this tournament maintains this academic standard that is so good. And also the volunteers. This year we have recruited on the order of 15 volunteers. They're all high school students. They're not as experienced with this competition, but I'm sure that through doing this competition as a volunteer, they've learned a lot about not only how to do the timing, but also something from physics as well. And we appreciate all of their hard work with timing, with organizing the Zoom meetings, and just sort of stepping up when someone is not there and taking over this role to make sure that the tournament runs smoothly. And special thanks to a few other people. One is Professor Jason Harlow and Saprit, and also Peter from U of C Physics. We've had long discussions with them regarding how to bring this tournament back in person. Although we haven't reached a complete plan, a complete consensus for this year, but I'm hopeful that in the future we can one day bring this competition back in person and to give everyone a sort of a unique experience that is truly of CaYPT. And next is my committee members. In particular, we have Jerry, who is the information team lead. Now he is the third generation information team lead, maintaining the system that we have worked on for now the 5th year. He's done a lot of great work doing this system work on the back end, trying to resolve issues and making sure that everything runs smoothly. And he was also the one that coordinated a lot of the volunteer work that people did. He gave credentials to people. He made sure that, when links don't work, he just sends a volunteer there and then gets everything fixed. And I really thank you for all the work that you put in. And also we have Ian and Jeffrey, who you guys have seen. These are the core members of our team, and they were participants from, I think, a couple of years ago as well, right? So it's great to see that you guys have grown greatly, not only in terms of the academics, but also in terms of leadership skills and just the ability to handle the situation and to solve problems, and to just be in front of a camera, be on stage and speak to this audience. I'm really proud of you guys. And this year, there's a lot of work that I didn't have to put in myself, precisely because we have the help of Ian and Jeffrey. And finally, I want to say thanks to our supporter, Meritus Academy, for lending us these Zoom accounts that enables us to run this. We've scheduled this meeting for 8 hours without hitting that paywall. And I really thank them for their technical support. And as all of you have known by now, CaYPT has hit a point where we are evolving, we are changing. There are obstacles that we have faced in the past years, and we are really stepping towards a new generation of this tournament. And I am committed to bring a team to Hungary this year for CaYPT 2024. we will be announcing some of the details of individual selection in the coming days, and we are just working on finalizing that. So if you guys are interested in selecting for the national team, please stay tuned for any email updates that we send, and we'll tell you how the rules work and how you can submit your work. And it's not finalized yet, but this year I do want to get some more juror involvement in the individual selection stage as well. So I'll be sending out the information for that later on. And if jurors are interested in like looking at some of your presentations again and assigning you a grade in like sort of peace and quiet of their own office, they will have the choice to do that. So thanks to everyone for joining us. And I will declare the CaYPT 2024 closed. And I hope to see you guys around, maybe in school, maybe at at individual selection or national camp or anything like that. And I hope you enjoyed this competition. And please go home and get some rest. It must have been a long week and a long day for everyone. Well, thanks everyone.
Yeah, thank you so much.
Thank you so much.
Thank you, everyone.
Thank you.
Thank you, Jim.
Good night.
Thank you.
Bye. Good night. Have a nice weekend.